Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
How are you all doing?
Hope everybody is good.
Yes.
I didn't jump to the podcast this week because I forgot.
That's okay. But just to let you know that we do have a podcast that
Yes.
you can watch on YouTube or listen on YouTube, as well as iTunes and Audible and Spotify and all the places where people get their podcasts, the common places at least where people get their podcasts. So welcome to another episode of Ask Us Anything About Electrochemistry. I'm Alex. This is Neil. We're two. I'm a chemist and Neil's a chemical engineer from Pine Research Instrumentation. I guess we've never actually
we never
told them what we
introduced
are.
that. Yeah.
Yeah.
We work at a company
just
and we
work
do
at a company.
electrochemistry all the time. So
Yeah. And we get a lot of questions from webinars and YouTube videos and all kinds of places. And this is kind of the opportunity for you to just ask us any question. We can go into more detail than we normally could on, say, a comment or typing out an answer or writing an email. So we can spend a little bit more time answering some of the questions that you might have about electrochemistry. So we usually run this live stream for about 2 hours. And if you're watching this later after the fact, if you can't make it live, there will be all the questions will be in the description. Timestamps will be in the description below. If there was a question that you wanted answered that you didn't get a chance to, you can just write a comment on this video, and then in the next upcoming live stream, we will try to address or answer that question. We apologize in advance if we can't pronounce people's names. We are broadcasting to Twitter and YouTube, so ask your questions there, and we'll try to get to them as quickly as possible. Please don't ask questions that are ultra specific to your research, like what is the bond energy of a very specific molecule. It's too specific for us to really know the answer. But similarly, don't ask us a question that's so broad, like explain everything about cyclic voltammetry, because that's also something that is more suitable for like a webinar or more long form content. But things where you want additional clarification on a topic that seems unclear or general guidance is the best. Those are the best kinds of questions to ask us for this format. If you are a tier 1 or tier 2 member, you can join us on Restream to actually show us some of your data. And thank you if you are a tier 1 or tier 2 member. Your membership actually just helps support the creation of this kind of content. So thank you. And I think with that said, that's all the boilerplate stuff that we go over. And it looks like we have a series of questions from George or Jorge, however you like to be pronounced. So we'll go through them because it's a lot. Let's see. So, okay. George asks, so I tried to make a design that represents the surface of the metal, the film formed on it, and the electrolyte solution. And continues, a system consisting of 2 interfaces, metal film and film solution. The model describes the growth of the film with the movement of ions inside through the vacancies, like a point defect model. So the question is, how should arrows indicate the movement of metal ions through the gaps in the direction of the electronic solution towards the surface of the metal or in the direction of the electrolyte? And he asks, he just says, thank you so much. So let's see. So arrows, how should arrows indicate the movement of metal ions through the gaps?
I think the tricky thing with this question is he's referring to like making a model.
Yes.
I've done some like I was mainly experimental electrochemistry, and when I was in graduate school and stuff like that, I did a little bit of modeling work with a few other things, not this specific kind of system.
Mm-hmm.
But I don't know, at least for me, I see this question, and part of it is that I'm not familiar with the point defect model. I think it's a corrosion specific kind of model, but I don't know, what it is really. I haven't used it. And so when you're talking about the arrows, I think you're just basically this process of a passive film forming on a steel surface, right? This is a corrosion process. Like I've covered this kind of phenomena with respect to impedance spectroscopy and circuit fitting. We can talk about linear polarization resistance and things of that nature. As it relates to what your question, which is related to like a modeling thing and sort of, the arrow of movement or something of that nature. I don't know that I'm equipped to cast a lot of judgment on that, to be perfectly honest, right? Even just from the perspective of how should the arrows indicate the movement. I mean, what comes to my mind is more like, well, you just have this diffusional behavior of ions in solution and towards the surface and the film growth. Like I kind of don't know what
Yeah.
purpose this right this has, and also just what does what does electronic solution mean? You mean the film? Like I kind of don't know 100% what that means.
Yeah.
So that's the most I can say about it. I don't know if Alex wants to add more content, but I don't have much more knowledge to add other than what I just said.
Yeah, I guess I am trying to understand a little bit more about the system. It does sound like I get the idea of 3 layers basically. You have liquid electrolyte, you have a film, and then you have I would say a solid conductor. That's what I believe it to be. That's when you said you have a system consisting of 2 interfaces, metal film, film solution. And I know Neil has taught me a lot from EIS that like you can have gaps in your film, and now your system actually becomes a little bit more complicated, because then you also have solution metal interfaces as well. I don't know if that's the case for your system, but assuming that that's completely full, I don't know what the film is. Let's see, because the growth of the film,
I think it's the passive layer. So I think again, this is what you're mentioning is that phenomenon that I've talked about when I do some of my impedance webinars or things like that. It's like the difference between basically what you would say is like a Randall series model and an embedded model, right? I can pull up a PowerPoint slide that just shows the difference of those two things very quickly. I won't spend forever on it, but the point of this to me that's tricky is actually more about, I guess I would say, the distinction between those models, but more specifically, if you're talking about arrows moving with a modeling, what you're talking about, a modeling is not likely the circuit fitting model, right? You're talking about like a mathematical model to describe the film formation, things like that. So you may not be referring to this, for example. This is from my impedance webinar. This is the series model. So you have a film, and this is the embedded model. I'm just sort of making them bigger, right? I wonder, did I have the film thing in this webinar? I might have to pull up a different webinar. Yeah, I'm going to pull up a different webinar. I have the one that shows the interfaces. It's a little bit better. I'm going to pull it up for you as well.
No, George, thank you for your comment. We really appreciate it. Also, if you can give us a little bit more explanation as well, that would also help us with at least trying to talk through this. I guess one of my questions is, so I'm assuming there's metal ions inside the film, and the ions can diffuse towards the electrolyte, but also diffuse towards the metal.
I don't know what electronic solution means. That might just be a bit of a terminology thing or a language thing. I'm not 100% sure. But the thing about the embedded in series model is the situation that Alex was referring to that I've talked about before is basically this, right? You have substrate, which is your steel. Your film is like your passive layer, and then your electrolyte. And if your film doesn't fully cover the surface, then you have some of the electrolyte that can contact the steel itself as well as the passive layer. And so basically you have processes that can take place either or both at the interface between electrolyte and film and substrate, and then possibly electrolyte and substrate. And so, as it relates to again, you're just talking about like how things it's like the growth of this film is an electrochemical process, presumably, right? There's some degradation of electrolyte or I don't know, oxidation of species on the surface of the steel, like formation of hydroxides. You're in KOH, so probably some sort of hydroxide or oxide formation on the surface, like something of that nature is forming this film on the surface. Like these are all just somewhat guesses here, but that means you have stuff. I mean, I presume, again, I'm sort of talking myself into trying to answer your question. Trying not to leave you hanging, but you have stuff working its way right from the solution to the surface. I suppose probably, right? I mean, you have to have some reagent work its way there so that you can have a oxidation reduction process occur, is my guess. But anyway, maybe we'll drop it from here because I don't know how much more we can really answer unless you
we need
either
more
clarify
information.
or
Sorry.
But I think part of the issue that we may not be able to answer no matter what. I mean, again, please go ahead and give some more details. Part of it we can't answer probably is because we don't have the intricate knowledge of the numerical modeling that you're doing per se, and to a certain extent, we're going to be handicapped by not having that information. And so, my apologies if we can't give you a better answer than that, I suppose. But it does sound like a pretty interesting system that you're studying.
Mm-hmm.
I wanted to just note this. This was a question that was just before we went live. So actually, chronologically, Enoch's question here was first. And he asked, what is the equivalent circuit for aluminum air and zinc air batteries? So in short, I can't answer this because I need to see the data. Like, there isn't an answer for the equivalent circuit for anything, really. To a certain extent, it's all interpretive. The answer to this is, what does your EIS data look like? So, Enoch, if you are here or if you're looking at this afterwards and you want to comment or something like that, I'm happy to kind of try to give you an impression about what I think a circuit might be based on how your data looks. And I know it might be hard to do so. I'm not looking at your data. We're the ones live showing you our screens. So it might be the trickiness of getting information across in that way. I appreciate that, the difficulty. The point is that I without seeing the data, I don't know how to I can't really answer that question, right? Generally speaking, I'll tell you batteries typically have a leading ohmic resistor. Sometimes there's an inductor, as well as 1, 2, or 3 Randall's elements, and then sometimes a Warburg element. It's relatively standard types of circuit analogs are typically used for batteries. But again, that's just a general answer for what most batteries tend to have for features. I would have to see your data specifically to be able to answer further.
Okay, looks like the next question is up your alley, Neil. In galvanostatic charge-discharge curves, what is the effect of current density on discharge time? Please explain with a reason.
Higher current applied during a galvanostatic discharge makes it take less time. So
makes sense.
Yeah. I'm not sure if you're asking a slightly different question. Something tells me you might be, based on the wording of this. And because you're talking about current density, it's not really the right variable for a galvanostatic charge discharge. It's just the applied current. A galvanostatic charge discharge test involves an applied current, which we usually call a C rate. Maybe current density, you're referring to like the milliamps per gram applied or something, I guess. I don't 100% know what you're imagining for a current density, but basically if your battery has 1 amp hour capacity and you apply 1 amp, it's going to take an hour. If you apply 2 amps, it's going to take half an hour. If you apply 4 amps, it's going to take a quarter of an hour. I have to do math as I do this, right? But as you apply higher and more current, it takes less time, right? And then similarly the other direction. So if it's a 1 amp hour battery and you apply half an amp, it will take 2 hours to charge it up. So it's like, how long does it take for that current to fill up the capacity, right? So the effect of current density on discharge time is that it's directly related to discharge time. More current makes it charge or discharge faster. Lower current makes it charge or discharge slower.
Okay. Yumna has kind of a follow-up, which is explain the shape of CV curves for capacitive and pseudocapacitive behavior of supercapacitors. I don't know enough about pseudocapacitors, or specifically, or I don't know enough about pseudocapacitance. I don't know if either of us really know enough about it, but I can explain just in general how capacitance manifests itself in a cyclic voltammetry curve. So I can just show you this. Hopefully this is helpful. I don't know if it will be, but so in cyclic voltammetry, you're looking at the voltage. Sorry, you're looking at the, yeah, well, actually, yes, that was right. Yeah, you're looking at the voltage down here, and then you have the current. And typically, if you have a capacitor, so actually, if you hooked up your potentiostat to a capacitor on one side in like a 2-electrode setup, and you were to sweep the potential, you'll probably get something that looks like this. It'll look like a box. And the so this is how I think about it. But the capacitance, the charge of your capacitor is equal to the capacitance times the voltage. And if you were to take the time derivative of this, you would get dq dt, which is equal to I don't draw that well.
If you don't draw well, what does that mean for me?
No, you draw much better.
That is a bold-faced lie, but please continue.
CT and then dv dt. So you kind of have this is what the equation is. So if you take the time derivative, the time derivative of capacitance is a constant, because capacitance is ideally not changing. Maybe it changes a little bit, but it's assumed to be constant for electrochemical systems. dq dt is current. dq dt is current. And dv dt is the scan rate.
I'm going to move the question out of the way.
Oh, yeah, thank you. Which is sometimes has like a little new or something like that. So the current response that you would observe in a cyclic voltammetry experiment would just basically be the current for a capacitor is proportional to the scan rate. And so as you go to higher and higher scan rates, and you use like something different, you'll actually get a larger and larger proportional current, or maybe you get a smaller one. You could have a smaller one, kind of centered around 0. So the thickness of this always changes. So if this was 0, it would just go around this way. And this is the ideal behavior of a capacitor when you're doing cyclic voltammetry. So you can actually generate this by taking a potentiostat, hooking up a capacitor to it, and you can generate this. Similarly, when you have if you have a redox piece, or if you have a typical electrochemical cell, and you scan the voltage in a region where there's no Faradaic processes, you'll get you'll actually get something that's slightly more curved. So let me I'll just I just need to let me select only this part. Can I just select this? Yes, here we go. What you'll find is that there tends to be a little bit of like a curve, like there's a little bit of a charging, and it discharges a little bit. So you'll end up seeing these curves all around the edges, and that's because you have some solution resistance. It becomes like an RC circuit. But that's the same kind of behavior, generally speaking, for a capacitor. And I would imagine a supercapacitor just has a much higher capacitance. These values
pseudocapacitor.
A supercapacitor has much larger values.
Oh, so you're just talking supercapacitor.
Supercapacitor.
Yeah.
That's my assumption. I haven't worked with a supercapacitor, and I honestly don't know enough about pseudocapacitance.
So I've just done a little bit of looking around here, because I also don't have a lot of experience with pseudocapacitors. But from the best of what I can find very quickly, and take this for what it's worth, I don't know that I can explain it all that well, but effectively, just like Alex said, nope, that's not what I clicked. This is what I clicked. Okay. Right. A capacitor is effectively, it's a rectangle. I didn't mean to draw a curve, but anyway, when you scan, you effectively get, whatever, it curves a little bit. So this is a capacitor, right? A pseudocapacitor will look basically like a capacitor, but it might be wavy, or you might have
Hmm.
defects, or it's just not perfectly flat. So this would be pseudo. See, I draw and write worse than you. So the point of this is, I'm not 100. I still don't have a lot of knowledge, like from a phenomenon perspective, exactly what a pseudocapacitor is doing as it relates to a capacitive effect, because it's more like, my world is more impedance, thinking through. And so when we have things that are capacitive but not behaving perfectly ideally, generally the explanation is to use a constant phase element and have your alpha be, less than 1, which is the majority of all capacitive elements actually behave relatively non-ideally, and we can describe that through heterogeneities in the surface. And maybe that's the answer to some degree. Like a pseudocapacitor is more of a capacitor that has some uneven surface defects, or something of that nature, perhaps. And effectively, what it appears is that the result graphically, which is basically your question, partly the shape of a CV curve, is that a pseudocapacitive behavior effectively leads to the capacitive CV, but it's not flat and stable. Not to the effect of a Faradaic peak, right? Because the pseudocapacitive behaviors, I presume, a non-Faradaic process, but I don't know that I can explain exactly why, other than to say that perhaps just the right surface defects or heterogeneities or something like that might lead to non-ideal capacitance, and otherwise I don't have a better, at least to this point, knowledge base to really describe the process of pseudocapacitance from a first principles or basic phenomenon point of view. I don't think I know exactly what that is, to be honest. But hopefully that's useful from just describing what the capacitance looks like in the equation that Alex mentioned there.
Yeah.
So do you know about this? I actually don't know what this is. Adarsh has asked, what additional information can you get from a derivative of voltammogram? What situation at the electrode interface reflects it? Do you mean just taking the
Derivative of
derivative
a
of
CV?
a CV plot? Like actually taking the derivative of a CV plot? That I don't know if that's what you mean. Because is there a, I don't actually know. Is there a technique called derivative CV?
Yeah, I don't know.
I'm actually not really.
Derivative.
I'm going to try something really quick in our software and see if it shows anything worthwhile. I'm going to take the derivative of a voltammogram, and if it doesn't look like anything reasonable, I'm not going to show you. But I'm not 100% sure. So, I mean, generally speaking, what I can say about a derivative, of course, is that it's like a measure of the change in the slope, right? That's just like definitionally what a derivative is.
Yeah.
So I don't know if there's something like the derivative, shows you where the slope changes. And so it is a way to, I don't know, observe where a peak is. So like here's something. I don't know how useful exactly this is going to be, but I can show you our software. So for example, these are just some voltammograms. It doesn't really matter where they're from. You don't have to know any specific details. It's not relevant. But to your point about, I'm just going to delete all the traces so it's not convoluted here. Okay, so here's like a voltammogram, or well, it's really an LSV, right?
Yeah.
But it's actually simpler. It's just one. So I'm going to do a differentiation with respect to the y-axis, I'm assuming.
Yeah.
Okay. Now the interesting thing, of course, is that the units change. This is now conductance or conductivity or whatever. Siemens is the unit, because the derivative is what it's the y over the. It's like the slope. It's y over the x. So you get. I mean, it's
rise over run.
Yeah. Right. So effectively, we can see what. Which one did I even do, to be honest? 40. I want to overlay it so we can see. I think it's this one. Okay, I'll just copy it. I'm going to overlay it. So I mean, I'm just sort of working this through on the fly with you here, but it's like
Yeah.
the mid, as the slope increases, that's right here, right? The slope is increasing, the derivative increases, and then the slope starts to decrease. And where the slope is 0 is the peak. So mathematically, it does actually make quite a lot of sense that if you're looking for a peak on a derivative plot, you're looking for where the slope is 0, because the slope at the top of a peak is 0, right? The line, the tangent to this plot right here at the top is 0. So where it's actually this point here, right, where it's 0 or close to 0, the derivative plot, that's where the peak is.
Yeah.
I don't know if that's exactly what you're asking for, and I'm not familiar with, I don't know, sort of commonplace set of analyses where people plot or report derivative CVs. Perhaps it's more common than I'm aware of, but yeah, you're talking about taking the derivative of CV. So yeah, anyway, I mean, effectively, I think finding the peak is finding where the derivative is equal to 0 or close to 0. That, that's either a baseline or a peak, because that's where the slope zeroes out. So maybe that's the answer you're looking for. I hope that's helpful for you.
Yeah. Sorry, I can't be any more helpful. I haven't used derivatives of CV plots before, so I just don't know how to interpret them. Let's see. Just going down the list. Yumna has a question: how to calculate charge transfer resistance (RCT) and series resistance (RS) from a Nyquist plot? Well, I think you've probably, I don't know if you. I mean, this is like hopefully like simple enough. You've done this like a bajillion times.
I'm trying to I'll find the slide where I show it. Hopefully that's just the easiest.
I think it'll make it fairly easy.
Yep.
And just looking while you're getting that up, looks like people are just saying like hello Mohammed and Gabe. Yep, feel free to ask us any questions. And if you're on Twitter, I know a lot of you on Twitter are watching. If you want to ask us, or X, however, Twitter, X, whichever.
It's always Twitter to me.
You can ask us a question, just type it in, and then we can respond. All right.
So here, this is actually a relatively straightforward answer for you. So how do you get RCT and RS from the Nyquist plot? Tell me if it shares full screen. Is it working?
Yeah, I'm gonna. Well, it's not sharing full screen, but
this always happens, right? How do I do that right? Did this happen last time? I feel like.
I had
you
were on Crowdcast, right? When you were.
No, I know, but didn't I have this issue with? Maybe I didn't. Maybe I haven't tried sharing full screen with Restream. When I go to like presentation mode, it like doesn't share it. I think that's the thing.
Oh yeah. So that might be part of the issue.
Maybe that's the issue. Somehow we've been doing this for a year and still haven't worked out the kinks. So that's great. Okay, so just down here in the corner, I'll zoom in for you. Right. If I have a Nyquist plot, this is like the simplest Nyquist plot you can imagine. Right. It's just a semicircle. But you can imagine whatever it happens to be. If I have a semicircle, the width of the semicircle is RCT, and the distance on the x-axis of my Nyquist plot from 0 to where the data starts is RS. That's the ohmic resistance. So this is an example with this circuit here, right? I just have 250 ohms of ohmic uncompensated resistance, whatever. So there you go. That's where that shows up. And then my Randall's element in a semicircle charge transfer resistance is 1,000 ohms, and so the width of the semicircle is 1,000 ohms. That's the answer. There's I don't have anything else to say. That's the answer to your question.
Yeah.
If you have a follow up or you want more, I don't know, elaboration on analysis or something of that regard, feel free to ask. But that's the direct answer to your question.
Yeah. Let's see, next question.
I think I hit it at the same time.
Yep. Yeah. All right. Manuels asks, good morning. When working with proton exchange membranes, what is the best technique to measure conductivity, and what type of graph best represents the behavior of the analysis? Best technique. I have usually seen people use a kind of like an H cell setup. I can just show something at least from our website.
I have another diagram if you want.
Oh, you have another diagram? Yeah, you can pull up the diagram.
I'm trying to find it.
I'm looking for our advanced H cell just to kind of
Yeah,
show
show that while
people.
I try to find it. Where did I send it?
So
Here
I'm
it
just
is.
going to share Chrome tabs. Here we go. So hopefully you can see this. This is our low volume membrane cell, and just making sure that it shows up on.
Bring up the
regression.
Lugan one. I'm gonna hide.
Oh,
the
the
question.
Lugan one
Yeah,
might be
bring up the
better?
Lugan one
Okay.
because I have a thing that goes with that.
So this is the Lugan one. But usually, let's see. So hopefully you can see this. Here we go. Yeah. So actually, this is a very good demonstration of the setup. But in this case, let's see. You can see that. Yeah. So this is the type of setup you have. So the membrane would fit in the middle. And normally and what happens here is your reference electrodes are on these kind of Lugan capillaries on the other side, and it goes all the way down. It gets actually very close to the and you can adjust the distance, but you can get these Lugan capillaries to be very close to your membrane. And this other one goes very close to the membrane. And then this would be like sometimes you maybe have like a working or a counter on either side. And this just allows like current to flow. But the reference electrodes represent the kind of sensing points. And to my knowledge, I haven't done very many conductivity experiments.
Yeah.
I've actually recommended people do impedance. And just the inverse of the resistance or the inverse of the impedance is the conductance. And impedance gives you information as a function of frequency. It's not just oh, this is conductive. It's oh, this has different conductances at different frequencies based on the material. So doing EIS and thinking of it from a resistance standpoint rather than a conductivity standpoint helps you understand. It gives you a lot more information about your membrane and membrane properties.
So I'll share a thing that's just piggybacking on that because it's using that
Yeah.
cell there.
Mm-hmm.
I had this. I have this in like an email I will send to people who are using this cell. So effectively, this is just the cell. Is it showing? I think it is, right?
Yes. Yeah.
So this is the cell that Alex was just showing, right? Excuse me. So basically, yeah, where you have two working counter, whatever you want to call it. Basically, you just have two platinum electrodes in the middle, and then you have the reference electrodes on the outside and the Lugan tubes. And so you have one side is the working sense, one side is the reference. Those are the sensed leads. Basically, the cross section is like this. You try to get the Lugan tubes as close as possible to your membrane. It doesn't have to be Nafion, it could be anything, right? And there's a distance between the openings of these Lugan tubes, these Lugan capillaries, basically. And so effectively what you do is you run either a short LSV experiment or you do impedance. Because yeah, exactly. It's what you're just trying to get. There's two ways to do this. And I honestly don't know what the right way is. It sort of depends on, I guess, what you're comparing it to. The inverse of resistance is conductance or conductivity. I think conductivity usually involves so Siemens is conductance, I guess, or I think that's technically conductance, right? Which is the inverse of ohms. So any which way you can get ohms, you invert it and you get conductance. And then I think conductivity is when there's a length unit. There's a weird thing with the length to me. This is always one of these things. The calculation of conductivity falls in the same category as some other things, in my opinion, that are hard to grasp because most of the time there's a length unit involved, and where that length unit should be is not always clear. So, for example, people use this. This is conductivity is L over RA is one possibility here. So the R1 over R, you have 1 over R here. So you get a Siemens as the unit, but it's L in the numerator and area in the denominator so that you get the per centimeter unit in there, basically, right? But it's like sometimes you'll see equations for things in this way or similar to this where they just call something like characteristic length. And it's like, well, what is that? Is it the thickness of my membrane?
Yeah.
Is it the length
The
across?
characteristic length.
Yeah, which is
What
it's just
that?
such a hard thing. I hate it because you'll have that for like getting a diffusion coefficient of some material. Okay, so just multiply by you need the characteristic length. Well, what is that? Is it the thickness of the film? Is it the
Yeah.
thickness of the substrate? Is it the
distance, just
distance,
between
the diffusion length, the distance?
Yeah.
Right. Like what, you just sort of pick one.
I
And then,
guess.
yeah. So I don't care for this. I'm just being sort of honest about this part of it being a bit funky to me. Right. But in any case, this is an expression and a sort of a definition L over RA that is used to calculate the conductivity. And for what it's worth, the area being the exposed area of my membrane, which is in the middle of your sandwiched in here and whatever your membrane cell allows. And then, to get R, like Alex said, you either do impedance, you can get a direct measurement of R, or you can do a very short LSV or CV experiment over a very narrow range, like 100 millivolts or 50 millivolts, 300 millivolts, whatever. And if it's right around OCP, it'll be relatively straight line. And if you get a straight line, the slope of that line is basically the conductance or the resistance. You're just using Ohm's law, right? So if you do a sweep, the tricky thing is you have other stuff involved, maybe. So how accurate is that? There's open questions about this, but effectively, this is how you would could in theory get a measurement of the conductivity. So there you are.
Yeah, just looking through. Let's see the next question. Hopefully that was helpful. A lot of questions come in. Kasim is asking, "Hello, guys. I would like to understand better the physical meaning of charge transfer resistance and double layer capacitance in a PEM fuel cell. Thank you very much." Well, I think I don't know if I can speak specifically about PEM fuel cells, but I think I can talk about just generally what charge transfer resistance is and double layer capacitance, because most of this has to do with just interfaces. So I think I can pull up a slide. Oops, sorry. Let me just pull up a slide. Let's see if this can help people understand just at least a little bit. But all right. So all right, window. Okay. All right. So hopefully you can see this. This is kind of a general diagram of the electrode surface. So what we're talking about is a conductive electrode, some kind of metal, and then you have a solution that usually contains ions, anions, cations, things like that, and there will exist some kind of this is at least when it comes to electrical double layer charging. So if you, for example, want to apply a positive potential to your electrode, you will start to attract negatively charged ions towards the surface. And then I guess if I kind of go a little bit further this way, this is just basic electrochemistry, but it should still apply to PEM fuel cells. We describe the distance that you'll have some anions near the surface that forms what's known as the inner Helmholtz plane, and the inner Helmholtz plane and the charge at the working electrode surface form what we call the electrical double layer, just kind of these two layers. And then the layer of, but this negative charge also attracts positive charge. So positively charged cations that are solvated also tend to approach the surface. And the kind of the plane of positive charge is referred to as, or the center of the plane of positive charge is referred to as the outer Helmholtz plane. And then from there, you have what's known as a diffuse layer. So this is kind of the physical picture I like to think of the electrical double layer, which acts like a capacitor in electrochemical systems. And one thing to keep in mind or think about, what's perhaps most important, is that the potential across the electrode changes as a function of distance. So this is the bulk electrolyte solution. The potential starts to drop off kind of like crazy, like very quickly, from what's being applied at the electrode to what's out there in solution. So it tends to drop off, and there'll be potential differences at the inner Helmholtz and the outer Helmholtz plane. And then the potential is not equal to what's out there in the bulk solution across what's referred to as this diffuse layer over here. The potential is actually very different. So that is the simplest explanation of the electrical double layer. And this forms at conductive electrolyte solutions a conductive surface, a conductive solid surface. So it can be metal, it could be glassy carbon, which isn't a metal, as well as some kind of electrolyte solution. So double layers will form almost no matter what. You just put a piece of metal in water, or if this could be in your PEM fuel cell, this will form. That's kind of the idea behind the electrical double layer. When it comes to charge transfer resistance, I'm just kind of going through if I talk a little bit about this in my slides. But charge transfer resistance has to do with it's a description of electron transfer from a molecule, like a redox active molecule, to the electrode surface. So the charge transfer resistance, in a way, is representative of how hard it is at a specific potential for a Faradaic electron transfer process to occur. So that's like, I actually have another kind of diagram here, but if you have a molecule, you have a HOMO-LUMO gap, an electron transfer will occur, and there's a resistance associated with it that's dependent on the potential. So if you do impedance spectroscopy, I can just close that. If you're doing impedance spectroscopy, you can calculate and determine the charge transfer resistance at different potentials, because at different potentials, depending on the potential of your Faradaic redox active molecule, you will observe, you'll actually get different charge transfer resistance values. So I know this isn't specifically unique to PEM fuel cells, but it's general enough that I think it applies to PEM fuel cells. Unless there's a part of it that I don't know about.
There's a part of it we all don't know about.
Yeah, maybe there's a part of it. Well, so let us know if you have any further questions or need additional clarification on it. Double layer capacitance is it's a very complex subject. People could teach classes on the whole thing. It's kind of crazy, but yes. Okay.
So Yumna has a good question here. Suppose we have a material X, current density of 1 amp per gram, discharge time of 1,000 seconds. And we also have Y with a current density of 0.5 amp per gram, a discharge of 1,000 seconds. Which is better and why? So I'll show you. The answer is X. It's like spoiler alert, right?
Spoiler alert. Okay.
This is a simple mathematics problem. 1 amp per gram times 1,000 seconds of discharge time times 1 hour divided by 3,600 seconds. That's the capacity of material X. This is X, right? So what is that number? 1 times 1,000 divided by 3,600. It's 0.278. Is that right? 0.2, yeah. So 278 milliamp. I'm just putting it into milli. Amp times hour divided by gram. Milliamp hours per gram. That's the capacity of material X. Material Y, you could probably already figure out what's going to happen here. 0.5, it's half, right? And all the other numbers are the same. So effectively, I'm going to get half the capacity. So if I have the same discharge time at half the current, it means that it is doing half as much work, half as much storage. It's half as good in some sense. Okay, right? And so this number is what, Just divide this by 2. 100 and something. 39. Rounding it, right? 139
Yeah.
milliamp hours per gram. So material X is the winner, has a more capacity based on the numbers that you suggested. I hope that mathematics is clear. That's how I'd answer that question.
Sounds like a great answer.
It's pretty simple. I don't have much more to say. That's it. You gave me whatever, an exam question.
Yeah.
I answered it.
Yeah. Very good. So actually, it looks like there's kind of two kind of follow-up questions with Adarsh.
Mm.
How can I eventually translate a potentiostat system to a system operated by a DC power source, for example, to do a bulk scale experiment or a pilot plant? Can I measure cell voltage from the potentiostat system and apply the same to the DC power source? These are, well, the answer to that, it depends, but generally speaking, no. So, so I guess the main I guess question or issue is with a potentiostat, you can use a 3 electrode system where you apply a potential, or when you apply potential, it's to the working electrode with respect to a stable reference potential. And so you can do some experiments where you're doing a bulk scale experiment, some kind of big thing, and you're electrolyzing something, and the potential that you're applying to the working electrode that's doing the thing is with respect to something that's not changing at all in solution. Now, when you move to larger scales, and when you move to just a DC power source, you're now working in a 2 electrode system. So, in that case, you don't have a stable reference electrode with which if I apply this potential, I'm able to get this reaction to occur. So that's probably the main issue. There will probably be a lot of trial and error, honestly. And I actually think I haven't done this, but I think a lot of people who do like large scale electroplating and stuff like that, first off, they have systems that are very simple. There's not a lot of other random things that can happen, and they almost don't care that much. They just need to have reproducibility. I think if you use a potentiostat to at least get a general sense of what you should be looking for to get your coating or your electrolysis to happen, then you may just have to apply a little bit more voltage, or maybe you need a power supply that just gives you a current, like maybe it's more of a constant current power supply, and just have it do the reaction. And you have to not care about the detailed specifics of what's the potential that you're applying. And the other thing that's going to be challenging is bulk scale things can have massive IR drops just from like solution resistance and things like that. So the effective potential of what's happening at the interface, a big interface, could actually be very small. So you could use the same DC power supply in like a small cell, and then when you scale it up, you may need a lot more power to actually, or a higher voltage to get the same kind of results. So, so that's kind of my 2 cents about measuring the cell voltage and actually moving from a potentiostat system to a DC bulk source type of thing. But another thing you may consider is if you're trying to do large scale experiments, and Adarsh, I remember you had spoken earlier about I think you were on our you watched our video about, or the webinar yesterday about how potentiostats work. You now have seen the potentiostat circuit. If you're building this up for like some kind of pilot plant, you just might need a handful of some operational amplifiers just so that you can put a reference electrode into your system, and then just be limited by the power. Like that's going to be your limiting factor when you're trying to do a large scale bulk pilot plant type of thing. And then you're going to deal with a whole bunch of other circuit problems because there's heating issues, you know, when you're driving lots of current. So those are a couple of things to at least think about.
I gotta tell you, I'm always limited by power.
Always limited by power.
If I just had more power, the world would be mine. I don't know. I'm just kidding.
Mhm.
You said I'm limited by power, and all I
He's
can think of
limited
was
by
like
power.
all I can think of was like you're delivering a movie villain line. That's what it
Yes.
sounds like, you know.
Yeah,
I'm just limited by
just
power.
limited by power.
If I have the right reference electrode and operational amplifier, my problems will be over.
That's right.
Sorry, I'm getting all dramatic here. Okay, there's a good question here from Pine Research. It's sorry.
Oh no, I just said yeah. If you're on Twitter, which a lot of you are, I'm actually quite surprised.
I'm in a goofy mood here. Okay.
Um,
Sports News has this a good question. I was going to actually try to answer this. Can you give a brief about frequency dependence of impedance spectroscopy and Nyquist plots, which is a Bode plot, or Nyquist, irrespective of temperature? So what I'll try to answer this by going through. I think this should work. I think I figured out how to share a presentation finally. This is it. So tell me if this is like the actual presentation.
yeah,
working.
yeah.
Perfect.
That's great.
Yeah.
But what was the trick?
You have to start the presentation. I grabbed the wrong one, so
Oh.
now I have to start over. Okay, but I did it. But you have in
it works.
PowerPoint. I grabbed the PDF version. I want the animations. I make animations for a reason.
Oh yeah.
You know,
Mhm.
go to waste if I don't use them. Okay, you have to start the presentation, and at the bottom you have to like switch to the get the taskbar so I can come back to Restream and share the presentation and not PowerPoint itself.
Okay.
The presentation's like a different window entirely.
Yes.
So there you go.
Okay.
That's just how this works. So I'll try to go through this for you basically, but essentially, if you think about a Randall circuit as an example for how does frequency impact the impedance that we get here, basically, this is the most common kind of thing that you have a circuit, right? We have a leading ohmic resistance, uncompensated resistance, whatever. We have double layer capacitance or interfacial capacitance, and we have charge transfer resistance, which is some of what Alex was just talking about, right? Question with respect to PEM fuel cells, but effectively these two processes are pretty ubiquitous and present, right? The current, if you think about this in terms of an actual circuit, right, which is relevant for impedance, the current can go one of two directions. It can go through the charge transfer resistance, which is called Faradaic current. That's the process we're studying. Or the current can go through the bottom pathway through the double layer capacitance, and that's non-Faradaic current. And that's why, a typical experiment has some combination of Faradaic and non-Faradaic currents, right? When we do cyclic voltammetry, for example, in a 3-electrode system, we have a baseline current, then we have our peak, and it's on top of the baseline current. That's a combination of Faradaic and non-Faradaic processes. And in DC techniques, we typically can't deconvolute those very easily. They are constantly happening at the same time. The Nyquist plot typically looks like this, right? I've already talked about how we have this sort of semicircle behavior. I'm going to skip that part because that's related to the other parts of the webinar I'm not getting into right now. I want to try to answer your question specifically about how frequency matters with respect to the impedance measurements. So this is a quick review of Kirchhoff's laws, which is how we add circuits up, basically. So a series combination of resistors or circuits, you add them up, a parallel sum. We take the inverse, 1 over is equal to 1 over plus 1 over, and then when you simplify it, you get this expression. So this is just a reminder of how we add up the circuit elements when they're in series or parallel. In this specific example, resistors, the impedance of a resistor is constant. It's equal to just R, whatever the R is. The impedance of a capacitor is 1 over j omega c. J is the imaginary number. I'm going through this relatively quickly because I'm not doing a full-fledged webinar right now. I do encourage you, if you want to see this whole content, this is the second week of 5 of my 5-part EIS webinar series. It's on our YouTube channel for Tier 2 members if you want to watch this in full in a little more detail. In any case, simplifying the overall expression for the impedance of this whole thing as a function of frequency, you get this expression. Okay, so here's the answer to your question effectively. And why impedance is powerful is sort of the lens through which I talk about this, particularly in the webinar. The frequency dependence of impedance allows me to probe both the resistance, the charge transfer resistance, and the capacitance, just depending on the frequency. Whereas with DC methods, I kind of can't do that very easily, right? Now you can see that the resistances are not dependent on omega, the frequency, but the capacitance is. It's inversely related. So think about this mathematically. What happens at high frequency if omega goes to infinity, right? So 1 over infinity is 0. So the impedance of this element here is 0, right? Now, what does that mean practically? Well, the current has to go from one dot to the other dot across this interface, right? So charge is being transferred across this interface, either through this resistor or through this capacitor. It's going to go to the path of least resistance, right? Well, this R is some number, but it's not 0. And this C is 0, effectively, right? When the frequency is really high. So all the current is going to go this direction. And so the current goes through this resistor, and then it bypasses this charge transfer resistance entirely. The other extreme, if the frequency is 0 or very, very small, right? Slow frequency, 1 over 0 is infinity. So this impedance gets very, very large as the frequency gets smaller. So the impedance of a capacitor is inversely related to frequency. The impedance here is very, very big. All the current is going to go the other way. And so basically, the changing of frequency allows me to change the pathway of current or charge, buildup, whatever, that I'm probing at any moment in time. It's all happening at the same time, but I'm only probing one of these processes at a time just by changing frequency. Okay. And so the effect of this on the Bode plot effectively is here, and the Nyquist plot is here, right? As frequency goes from low to high, it's backwards on the Nyquist plot. The Nyquist plot going from left to right is high to low, right? And so as the frequency, you can look at the overall mathematics here, and this is the last thing that I'll say about this again, because the rest of all this context is in my webinar itself, but mathematically, numerically, I should say, this is how it impacts the Bode and the Nyquist plots. As the frequency is really, really high, as I said, it bypasses the charge transfer resistance. It goes all the way through this capacitive element that has almost no impedance whatsoever at high frequency. But mathematically, we have 1 plus RCT omega. So omega is still in the numerator here. So as omega goes really big, this term goes away. And the impedance at infinite frequency, or the highest frequencies, is just equal to Rs. So in the Nyquist plot, this is also the answer to a question I answered earlier, which is to say that the ohmic resistance, uncompensated resistance, series resistor, whatever you want to call it, is the high frequency input on the Nyquist plot. And on the Bode plot, it is basically, typically you get something like this. Not every system behaves exactly the same, but if you have a system like this, the plateau of the impedance magnitude at high frequency, that is all equivalent to the series resistor. Okay, and then at low frequency, this term goes away, but I still have a 1 here. And so at low frequency, the rightmost intercept basically is equal to Rs plus RCT. So the plateau in my impedance magnitude plot, if I have one, if I have a perfect system like this, which doesn't always happen, but typically you have some plateau or close to a plateau in the Bode plot, and that is equivalent to the sum of those resistors, which means that by subtraction, right, the semicircle width is equivalent to the charge transfer resistance. So we have series resistance, charge transfer resistance. There's a way to calculate the capacitance. It has to do with the peak frequency. It's a bit funky, but it has to do with the time constant as well. Typically something like 3 to 6 time constants is this total time it takes to charge up this capacitor through as part of this at the surface here. I'm not getting into this too much more. Again, more context, see the webinar. But calculation of the resistances is much more convenient, let's say, from the Nyquist plots or even the Bode plot themselves directly than calculating the capacitance, though it can be done. But most frequently, people use circuit fitting to get a measurement of that capacitive value. So that's like think that was 10 minutes, 8 minutes of an hour-long webinar I tried to get through quickly. So we don't take all day, but I hope that answers your question, sports news, about at least some of the aspects of frequency, what it has to do with impedance results.
All right, very good. May have another, maybe this is another kind of battery question from Knock22. Knock22. What is the difference between supercapacitor and battery in terms of capacity? Is a battery can store charge more than a supercapacitor? What if battery loses its capacity fast? Is this good? My very limited understanding of this, I don't know if there's necessarily like batteries and supercapacities fundamentally have major differences in capacity. My understanding is about kind of how they operate, and from a functional perspective, supercapacitors and capacitors can charge and discharge very quickly, while batteries charge and discharge much more slowly. And that can be useful for a variety of different applications that you may have. Sometimes you need something to just last for a long time, like your phone. But sometimes if you're driving a car and you need to accelerate and get a lot of power, for an electric car at least, to get up to speed on the highway, you need to discharge very quickly. And so a capacitor would be a better application of being able to discharge very quickly and getting a lot of power very fast in a short period of time. So I don't know about fundamentally whether the capacity of I guess you could always do a calculation, I suppose, and use just the voltage across a capacitor and its capacity to determine the charge, and then I don't know, integrate a charge discharge curve to figure out the total capacity of in coulombs.
I don't know, to be honest, actually, like if commercial capacitors or supercapacitors routinely have higher capacity than batteries of a similar usage. It's exactly what Alex said. It's more of a usage case. So capacitors, as you said, are used to deliver energy very, very quickly, usually, right? They can. I think capacitors can store. Maybe there's some arms race here. Capacitors are losing by a few amp hours per gram. I don't know. And it isn't to a certain extent relevant, because just you can make more batteries or put them more in series or parallel, or make them bigger, more surface area, whatever. So it's like maybe the specific capacity for batteries writ large are better than capacitors or something, but they each have their place. It isn't really a competition in some sense. They're actually both storage devices are kind of used for different purposes, which is just what Alex said. And then, I mean, to your last point, if the battery loses its capacity fast, that's probably not good unless you are discharging it really, really fast, in which case it's probably just it's discharging. Like if you have a battery that you're pulling a ton of current out of really, really for a fast, discharge, well, then of course it's going to lose its capacity, or it's going to lose its charge, I should say. So if it's losing its capacity fast, like if you're doing charge discharge cycles, like 100,000 whatever charge discharge cycles, and its capacity is dying precipitously over that, stability kind of test, that is bad. That means your materials aren't stable. They're probably degrading. You're probably forming non-conductive, orphan kinds of species. Possibly you're losing intercalation, deintercalation ability. There's a lot of possibilities. It depends on what the materials are, but most probably, the materials or something about the construction of the battery is flawed, and it's not functional over a long period of time. So yeah, that's which, to be honest, like, it depends on what you're doing. If you're looking at a commercial battery, that's really quite bad, right? But if you're doing research, it's not bad from the perspective that you're getting an answer, right? Research is, it's like,
it wouldn't be research if you knew what you were doing.
Yeah, exactly. Also, I heard a funny Jim Gaffigan joke. He was like, he's had his appendix out, and he's making a joke. He's like, science doesn't know what the appendix is for. He's like, how is that an answer? He's like, we don't know. And it's like, it's funny.
Yeah.
Jim Gaffigan's a funny comedian.
Yes.
For those who don't know, he's very funny. But I had funny listening to it, because I'm like, that's a funny joke, but actually, Mr. Gaffigan, that is an answer.
Yeah.
It's a perfectly acceptable answer. There's a
Yeah.
lot we don't know, right? Like that's the purpose of research. So from that perspective, all I wanted to say was like, if you're doing research, I don't know, maybe you're doing research on battery materials, you're constructing batteries and you're finding this or that about them. And one of the things you're finding is that your materials are terrible and they're dying and their capacity is going away. Like that's an answer, right? You can even publish a paper with that saying, you know, like why you shouldn't use this material for battery material, you know, whatever, for battery electrodes. Like that is just part of the collective knowledge scientifically that we're all after, right? That's like the proliferation of scientific information is a net positive for humanity. This is like my, you know, go get him speech.
Go get him
you
speech.
know? But I'm serious. Like there's truth to that, right? Like just adding more knowledge. So if you publicize or make known or whatever that this particular material did not perform well as a battery material, you're saving someone else down the line the hassle of having to also investigate a material that isn't worthwhile, something like that, right? So there's value in a negative result. And you're learning something, hopefully, if you're doing research, right?
Yeah.
So there you go. That's my feel-good speech.
Yes. So there are a few questions in a row from Yumna, and I believe they had to do with when you were describing a Nyquist plot.
Yeah, I can see this. Where did 250 and 1,000 come from? I made them up.
Yeah.
Yeah, I was showing you, for example, on the plot, and I just showed it again in the little you know, short thing I did on frequency there. I just made it up. It's a complete made up example. I just showed a Randall's circuit and I just said, hey, if I put 250 here and 1,000 here, this is where it shows up. 250 is that first distance and 1,000 is the width of the semicircle. I just, those numbers just came out of nowhere. They came out of my head.
Yeah.
Okay. So that's where they came from. So yeah, it's not an indication that every Nyquist plot should have those numbers or anything like that.
Yeah.
That's not the thing. And then what if a Nyquist plot doesn't have a semicircle? Then you don't have a charge transfer process, probably.
Yeah.
Or you are not at the right potential to drive the charge transfer process, right? Because impedance is very potential dependent.
Yeah.
So if you have a Nyquist plot with no semicircle, it could just have capacitive or diffusional behavior.
Yeah.
Typically, if you have just kind of a lagging line that goes off forever or something like that, you might have uncompensated resistance and capacitance / diffusion. Yeah. Or pseudocapacitance, right? Or non-ideal capacitance, something, you know, if a perfect capacitor is like a straight vertical line.
Yeah.
And then a
perfect resistor is just a dot.
Yeah. Perfect resistor is a dot. And
on the x-axis.
Exactly. And then a non-ideal capacitor would be like a straight line, but at kind of an angle. So it's going off. You see it on the camera, like this is vertical, and then it would be at an angle with the x-axis, right? Something like that. So those are all, again, also not alarming, right? You don't always get a semicircle. It depends on what you're studying.
Yeah, that's true.
So user says, tomorrow is your lecture class. Why did we go live today?
So we go live every Friday, but as many Fridays as we can.
Yeah, that's right. Actually, that brings us to a point that, is it 2 Fridays in a row? No, next Friday at least we won't be.
Yeah, next Friday we won't, but the following we will.
Should be okay.
And if you by chance are in New Orleans for the ACS meeting in 2 weeks, we will be there.
I guess it's less than 2 weeks now. Right? It's a week from Monday. A week from this coming Monday, so it's like a little less than 2 weeks.
Yeah.
It's not next week, but it's the week after.
It's a little more than 1 week.
Numbers are hard.
Yeah.
Come see us at ACS. Alex and I will be there.
Yeah, and if you just happen to be in Houston, well, I don't know if you come. We're doing a workshop at the University of Houston, but we're already like full, like at capacity. So it's like I can't do it this next time. So, but yeah, I don't know. You can continue to ask questions. If your class is tomorrow, it's great. Now you're more prepared. So ask a question, user.
Also, I don't know. You have class on a Saturday. That's actually quite impressive.
Yeah, that's good.
Yeah,
it's very smart. Let's see how to build with Lego bricks.
Oh, I can answer that question. Oh, that's not the question.
That's not the question.
That's the name. I'm sorry. Yeah, I was getting excited. I want to talk about Legos.
Yeah, I know. What practical information can I get from EIS for improving the design of my device? For example, can EIS tell me if the surface of my electrode is not homogeneous or if the membrane is damaged. Practical information from EIS. Well, I mean, we just spoke about. So I think in general, in electrochemistry, you're always going to get values like current, voltage, resistance. You can measure capacitance, things like that. Those are the values that an electrochemistry experiment gives you. It's the interpretation of them within the context of your system that will provide you with evidence for why something is or isn't something. So Neil just explained, like,
Yeah.
you can calculate the solution resistance. That's like a value you can absolutely measure with EIS, but it's not going to necessarily tell you that your electrode surface is homogeneous or the membrane acts or behaves in a very specific way. You have to extrapolate that information from the EIS.
Yeah.
think.
I mean, it's the way what you said is what I was going to say.
Yeah.
I was going to word it in some way that it's kind of like, it's like what you're talking about is like a downstream effect,
Mhm.
which is to say, you're making an inference, an intelligent inference that I make the design of my device a certain way.
Yeah.
I have a membrane or I have this or that. When I do impedance, for example, if I have a membrane and an anode and a cathode, like if it's a
Mhm.
fuel cell, if it's a PEM, if it's whatever it is, doesn't matter. But in the case of a membrane and an anode and a cathode, EIS can usually get me the impedance of each of those things by themselves. Like it can get you the impedance of the anode, the impedance of the cathode, and like diffusional effects in the membrane or something like that, right? And so while it's probably not going to give you some kind of answer like membrane bad, fix membrane
Mhm.
necessarily, if you do impedance in different conditions, different times, different situations, and you notice that like the diffusional calculation that you get from your circuit fit, your diffusional analysis, your Warburg constant, or
Mhm.
just visually the impedance is going up or something, that can tell you, oh, well, the membrane is probably having problems because this part of my impedance plot, right? Now, how does that translate practically? This is where it's like a
Yeah.
step removed. It's like you have to infer, well, maybe what should I fix? Like,
Yeah.
the impedance isn't going to say like, well, you need to fix like this exact part, it's
Yeah.
just giving you the scientific results,
Yeah.
from what's happening. But it can, because impedance can pinpoint specific processes, in some cases you can check whether the resistance or the capacitance of this particular process at this frequency is changing more dramatically than another. Like you might have like two semicircles of just for example, and one of the semicircles is always the same and the other one's getting bigger, so it's like your resistance is getting worse for just the cathode instead of the anode, and so maybe you have like a delamination happening, or maybe
Yeah.
so
Yeah.
something like that is how you would probably use that information.
Mhm.
In particular from EIS, that's otherwise it isn't, sorry. The other thing that came to my mind was, um, for instance, with batteries, impedance can be used for state of health diagnostics. This is entirely empirical. So there is a possibility you can do something where you like find one of the variables, for instance, of impedance, like the imaginary impedance or the impedance magnitude or the phase
Mhm.
angle, at a particular set of frequencies or a particular set of conditions, and you can make a correlation, right? An empirical correlation, like like by temperature, right? Like at 50 degrees, this is what it gets. At 60, at 70, you make a calibration
Yeah.
curve, and then you can like use that to probe if the temperature has gotten too high, or I mean, so
Yeah.
those are some things you can do with impedance, kind of like you could do with anything, right? But
Mhm.
impedance is pretty nice. It's quick and non-invasive.
Mhm.
So other than that, though, right, you're mostly taking the data that you get from impedance and doing as much as you can to infer, well, this is with respect to the cathode or the anode, and so that's the thing that I should look to change or fix or whatever. But exactly how, right? Like it's not going to be easy always to tell you without your own interpretation, your own sort of intelligent analysis. Well, what's damaged and how? That's kind of up
Yeah.
to you, right?
Yeah. Yeah. Absolutely. It's like practical information. It's like,
Yeah.
what practical information? No, it's a good question. Erwin has kind of an interesting, maybe a little more clarification. It just says linear regression with cyclic voltammetry possible. I think it's just saying, can you do a linear regression of cyclic voltammetry? There are ways of taking data from a cyclic voltammogram and plotting a linear regression. For example, if you did multiple cyclic voltammograms varying the scan rate, and you were looking at the peak current, there's what's known as the Randall-Sevcich equation, and that's a linear regression of peak current values from cyclic voltammetry that allows you to extrapolate and calculate things like the area of the electrode. The diffusion coefficient is the most commonly is the common way of using it. So just from one cyclic voltammogram, I don't think so, because there's not really not too many purely linear things that are going on in the whole cyclic voltammogram. So maybe if you want to give us a little more clarification about exactly what you want, but that's my 2 cents about linear regression with cyclic voltammetry. Yumna has I think a few comments. I don't know about this. No, my question was not talking about mathematics. It was asking about the science behind it. He asked this question about half an hour ago, and I don't remember what exactly
Was it? I don't know if it was with respect to.
Was it like the battery capacity?
Oh, maybe
thing?
it was the battery thing.
Well, if you're just giving us material X and material Y, and you're just giving us numbers,
the science behind it. So the science behind it is actually still answered by the mathematics. I mean, I hate to sort of just repeat the same thing that I said, but if one material, so if the presumption of your question is that 1,000 seconds is what it takes for you to take a material that's at 100% state of charge, so it has all of its energy to give, and drain it completely to zero, it takes 1,000 seconds exactly for that to happen, right? That's like a third of an hour, whatever.
Mm-hmm.
And one of those materials drains out at a rate of 1 amp applied continuously, and the other one drains out at a rate of half an amp, then again, scientifically, mathematically, sort of whatever, however you want to make this interpretation, the one that is draining with an amp of current is giving you more energy, because it's not 1 amp, it's minus 1 amp. This is a directional thing, but you're getting an amp out of it. If it's discharging, it's giving you current, right? It's giving you 1 amp continuously for 1,000 seconds. Whereas the other one is only giving you a half an amp for 1,000 seconds. So it's like, if you were to take the second one and give you the same current, an amp, it's only going to last 500 seconds. It's going to last half of the amount of time, or even less. But basically, I hope this is clear. I mean, I don't know if I know how better to answer it than that. It's the amount of current that you get out of a battery material is the electricity. It's right, like it's the flow of electricity with respect to time. It's amp is a coulomb per second. It's the charge you're getting. It's the energy you're getting. It's the usefulness of it. If something's giving me a nanoamp, I can't power anything. It's going to take me forever. I can't run my phone on a nanoamp, right? But if I have an amp, I can do all kinds of stuff. And if I have half an amp, I can do some stuff. And if I have a tenth of an amp, I can do less stuff, right? And with all the time being equal, the one that's giving me more current is better, right? I hope that's clear. Is that if you still need more clarification, please let me know. I'm running out of ways to explain it. I think that is about as much as I can do. I like this question actually a lot, because it's numerical, it's concrete, and it highlights just these sort of fundamental calculations of battery. And analyses or units or something. So it's
Mm-hmm.
a good question, but if that isn't clear enough, please let me know. But I'm not sure how better to express it. I've tried to kind of come at it from a few different ways now. I hope that's clear.
Mm-hmm. And then even it has another a follow-up, I guess, question. Why capacitive behavior is called non-faradaic? Does it mean no redox reaction is taking place inside the cell? Correct. I mean, so capacitance. So a faradaic reaction has to do with an electron transfer across a liquid-solid interface. And so when we have things like double layer charging and it's capacitive, there's charge buildup on two sides, but they don't neutralize each other. It's not like the negative charge shoots an electron off to the positive side, and then potassium, K plus, or whatever the cation is. It doesn't become just potassium. That charge transfer does not occur. So that whenever there's an electron transfer, that is a faradaic process, and the movement of the ions is movement of current. It's the charging of the capacitor that does not involve any electron transfers. So there's no electron transfer that's occurring in a capacitor for that kind of system. So hopefully that clears up like definitions and some stuff like that. Okay, so you says that yes, it's clear now. That's good.
Okay.
Okay.
Perfect.
All right. That's good.
So this is a good question. Can electrochemistry fix my marriage? Yes.
Skew. Yes.
Yes.
Explain.
I have to explain.
Oh, I don't know.
I didn't expect to have to explain.
Yeah, I don't know. Can electrochemistry fix my marriage?
So I got to tell you, I'm trying really hard to come up with something very punny, and I just this requires a good dad joke pun response to it. Like only if it's electric, or I don't know, something very cheesy. There needs to be a cheesy answer, and I just
truthfully,
I can't come up with a better answer.
You need to, instead of just giving your wife I don't know, just give them a ring. It's not just a ring; it's a rotating ring disc.
There we go.
Ring disc. That's what you
that's
need.
good. Yeah, take that ring and rotate it, and measure peroxide. I don't know. I'm out.
And truly, if your loved one finds themselves in like a weird situation on a deserted island or something, a platinum ring has much more catalytic activity than a gold ring.
That's true.
It's probably going to be more useful.
Yeah, go with platinum.
Go with platinum.
Definitely go with platinum.
Absolutely.
So yes, there's a recipe to fix your marriage.
Yeah.
Oh, that's phenomenal.
That is funny.
Okay, Shrajib has a question.
Yes.
Is there anything? Oh, I think we both hit it again.
Yeah. Okay.
Is there anything to do? Kotechi-Levich and aftermath to calculate the value of n automatically. So no, not automatically. There's still a manual aspect of this, for sure. You'll need to, and that's one of those things that, to be honest, it's a tricky thing to automate for a lot of reasons. Some of them are hard to kind of explain because it's a coding thing and whatever. But even then, I would not be in favor of this from a programmatic and like selling it perspective, because doing Kotechi-Levich analysis is a lot of interpretation on your part as the researcher. I did a whole webinar on this, right? And there's definitely some part of Kotechi-Levich and TAFL analysis that just requires the researcher to cast some judgment on the data, right? What potential windows are diffusion limited and transition regions and those kinds of things. It's a dangerous thing to me, in my opinion, and I might, not be everyone's opinion, but it's mine, that to have software just make all the decisions for you. Like, I know we have peak height tools and we have these kinds of things, and okay, I understand that for sure. But to a certain extent, a lot of these kinds of complex and I mean, frankly, useful analyses
Mhm.
from the point of view of learning, like it's a, you learn something when you do Kotecki-Levitch analysis. You learn how to do it. You learn kind of what's going on. I wouldn't really want to have that so automated to the point that it kills the pedagogical aspect of it, to be perfectly honest. I do understand wanting to do it quicker per se, but yeah, I think there's value in doing those kinds of transforms and analyses yourself, because you really grasp the concept better. And if that's really the point, right? Is you're trying to understand what's happening with your electrode and your system and everything.
I guess I'm just curious about to calculate the value of n automatically.
Yeah,
like
that's TAFL.
so it's going from Kotecki-Levitch to then generating the TAFL plot, and then that's the TAFL plot that they're gonna get the n value.
N from, yeah. All
Okay.
of that, like I said, requires the researcher to choose the right voltage range for their TAFL plot for one reason or another. There's a lot of reasons why you would choose one thing or another, right? It's like it's the similar kind of thing happens with respect to circuit fitting. Like can you just automatically circuit fit and pick a circuit for me, do the fit, give me the values? And it's like, at a certain point, like, are you doing anything as a researcher? Are you learning anything? And are you actually applying something that you know about your system for real, something actually going on physically at the surface, chemically, phenomenologically, to do analysis and learn about your system? Or are you just looking for a quick solution? And I guess cynically, perhaps a lot of people are looking for the second one, but I disagree with it philosophically. I think there's value in doing this yourself. I think that these techniques, the more we automate everything, I sound like a very old person now, but the more we automate absolutely everything, we stop learning why or how to do it. And I don't find that to be useful.
Mm-hmm.
It's my opinion.
Mm-hmm. Mohammed has
Yeah, he had asked a question earlier, but I think he understood that it was an electronics question. It was sort of beyond the scope of what we know, I suppose.
Yeah, and I think this one's probably maybe
Similar,
also beyond the scope of what we know, which is, can we reach a point of controlling static electricity and use it in our daily life?
I mean, if you rub your feet on the floor and zap somebody, I guess that's using it in your daily life, right?
Yeah. Yeah, well, there you have it. You have an example right there. Just
wear socks, rub your feet on the carpet. You'll build up static electricity, and then touch your brother or your sister and annoy them, right? That's using static electricity, I guess. I always hate that. I always hated when I was a kid. I used to, do you ever like, if you're running around in socks, like as a kid in your house or something like that, and you touch a doorknob and it zap you. And
yes.
Always like freaked me out I always hated it. I would always like, touch it like quickly, so they would try to like discharge the, or like if I'm even this thing, like these
these fleeces,
whatever, when I'm putting it on, sometimes I'll hold a metal door as I'm putting it on.
Okay.
Because it won't, I'm grounding myself, right? It won't build up charge. I hate static electricity.
There might be some researchers who are going to try to utilize static electricity to maybe charge a device, but
it's not a lot of current out of that.
It's not a lot of current.
It's a cool idea though. It's like free, right?
Yeah, it's free, basically. Or just natural movement. But anyway, that's our 2 cents. Yumna has a follow-up. He says, is there any effective concentration of electrolyte solution on electrochemical results like CV, GCD, EIS? And he asks, because for my research, I am using 6 molar KOH electrolyte, but I think this is too concentrated and affects my results. Yes, concentration of your electrolyte solution will definitely play a result on your CV and GCD and EIS. Concentration of the supporting electrolyte just in general. It changes the capacitance of the double layer. In some cases, I've heard that it actually affects maybe the selection, but also concentration can affect kinetics of reactions that are occurring. So it can definitely get complicated, and with KOH in particular, it's very strongly basic. So that may also, it depends a little bit more on your system. But yeah, I think in general, yes, the concentration of your electrolyte definitely will affect your CV, GCD, and EAS results.
Yeah. I mean, I guess I don't know. Is it like a thing where would there be I don't know what you call like diminishing returns? Like
Mhm.
as the electrolyte concentration gets higher, your double layer capacitance would get thicker,
Um,
right? Or
the capacitance, I believe, increases.
yeah, would it
You
maybe not
know,
thicker, but at least
it's
increases?
it's in this
Yeah, look it up
book.
if you can. I guess if it's not too.
It gets weird.
Because my question is that like eventually at some point it feels like if the concentration of electrolyte just gets so high it would like plateau or something maybe, or maybe it keeps growing because I'm just 6 molar KOH is quite right. That's the really strong basic kind of tests that you're doing. So I guess my wonder is if you're just saturating so much like KOH in your solution, there might be some kind of like steric interference, or it's almost like physically getting in the way of other redox species or something like that. I mean, I don't know. I think it's possible. I don't totally know though. Or if the double layer is so thick or you know concentrated or whatever, right? That like the double layer capacitance is just like unwieldy. You know what I mean?
Yeah.
I'm not entirely sure about that, but I think there's something to the idea of having really concentrated electrolyte getting making things kind of crazy.
So this is from chapter 14 in Bard and Faulkner, the third edition. Sorry, I zoomed in a little bit too much.
Yep.
This is a figure, and it's basically saying that the capacitance on the left hand side. Oh God. Jeez. The capacitance on the left. I need to decrease this. Yeah, I need to. Let me just do that. Predicted differential capacitance from the Goy-Chapman model theory, calculated from the indicated concentrations of 1-to-1 electrolyte in water. The vertical and horizontal scales are are greatly expanded versus those in this figure because predicted capacitance rises very rapidly from EZ, which I believe is this value right here. So yeah, so this is also to say that the capacitance can also change as a function of the applied voltage, but it also shows that the capacitance changes as a function of the concentration. So that's at least to say a few things
Your background
about it.
current might just be growing to some really crazy effect, and it is affecting your results. Like you have a huge amount of background current from
Yeah.
the capacitance.
Yeah, so that's at least a thing. Again, like electrical double layer can be that can be taught that could be a course just in and of
Yeah,
itself.
and I mean think about it too from the perspective of a time constant, which is basically resistance, effectively like R times C. So
Mhm.
as your C is really big, it can take longer for the capacitance to set up,
Yes.
and it might be like basically nothing actually can happen until the double layer sets up on your electrode. And so
Mhm.
I don't know that this is like seconds and minutes, but it could be if you're starting to try to do some experiment and the double layer is taking a while to get set up. I don't know what a
Mhm.
while means, seconds, milliseconds. Again, this sort of, I'm just spitballing numbers here, but if it's taking a while for that to set up, it could be delaying or impacting the process that you're trying to study, right?
Mhm.
Whatever Faradaic process you're trying to study CV or charge discharge or impedance about.
Mhm.
The sluggishness of the capacitance setting up because of how big the capacitance is, because of
Yeah.
how concentrated your electrolyte, all of that might be whatever cascading into causing you some issues. Yeah. I
Yeah.
think that's definitely a possibility.
Mhm. Yeah. Yeah. Well, hopefully that was helpful.
Yeah.
I think that is all the questions we've
Do you have
had
any in
so
the queue
far.
that you
Oh
wanted
yeah, that's right.
I think there was one. We like never,
Queue.
we don't always get to it. We try to answer the ones live, obviously, but
Yeah.
But if you have some, there was one seated, I guess. Actually, I don't know if you want to talk about. We had like from 3 weeks ago or 2 weeks ago, you were going to talk about the
Oh, the whole
double layer setting up thing. I don't know if you want
Yeah.
to get into it. It's a lot, but
Yeah. It's whether or not people yeah, we can get into it. It wasn't a question. It was just based on conversations that we've
right.
had.
But it's
it's not
fascinating. I
bad.
thought it was fascinating.
It's definitely fascinating. Let's see. I think this was a question from Ricocchetti 9911. In CV duct-shaped curve, we always see a shift of reduction peak towards the left side compared to oxidation. In principle, both should happen at the same potential, right? So there is a little bit of kind of confusion, at least. So we don't know exactly, like, okay, left versus right side in potential depends a little bit, I think, on which convention you're using. So I'm going to use the IUPAC convention, but interestingly enough, you're seeing a shift in the reduction peak compared to oxidation. In principle, both should happen at the same potential. So that is correct, unless there are some other reactions that could be happening, especially if you say have a oh god, let me see. Let's see. Well, let's actually play around with this. We're gonna just do some experimentation. I have no idea whether or not this is gonna work or not. I haven't
Simulate it.
Yeah, I'm going to try to simulate a situation where, so I'm going to simulate a reduction reaction. And actually, usually an EC mechanism is what typically happens, or what can cause this kind of issue. So let me just simulate this. So this is a case where I have A getting reduced to B, and the reduction reaction is here. It's around 0 volts. And this is shifting around a little bit, but this apparently is not shifting around. So I don't know enough about why, but usually when you have this kind of reversible systems, usually they move together. So I'm going to switch this. I'm going to actually just make it an irreversible reaction. I'm going to simulate it, and oh, that's way too fast. You have absolutely nothing on the other side. Let's simulate that. So now that's a little bit more normal. I'm just going to keep an eye to see if I can get this to shift a little bit more. Another thing that could happen, another thing that could actually shift it, now that I think about it, is alpha. Alpha may actually be something. So if you have, I'm actually going to remove this. I'm going to delete this. So I just have an E reaction. Simulate, get something more normal. And I'm going to see whether or not I can, I need to usually, you don't see effects of alpha unless your electron transfer kinetics are slower. So just make it a little bit slower. And then I'm going to move this to see whether or not, let's see, I'm getting a little bit more current. So let's go to 8. It rescales a little bit. Let's see if I go to like 0.2. Not too much. I think, let's see. So if I make this even slower. Okay, so this seems to do it. So if, all right, so this may be a way of doing it. So if I have 0.5, so the E naught is 0. Both of these are shifting away, and I'm adjusting the heterogeneous rate constant. So both of these are kind of in good alignment when electron transfer is fast. When I make it slower, they both kind of shift. But if I make the reaction the alpha change, which is the transfer coefficient, one actually shifts a lot more or changes more so than the other one. This one actually looks more normal. So there may be a small element, like this is much closer to the E naught than this guy is. That could be one reason, which is rare. It's kind of hard to get voltammograms that look a little bit like this, but this is one reason why this might shift, and this one, the oxidation, does not shift around very much. You have some slow kinetics, and the alpha transfer coefficient is actually not as, this guy's shifting, this guy's not shifting quite so much. The alpha is actually in favor of one side versus another. So that is one way. I'd actually have to see the voltammogram specifically, but you could play around with this with Aftermath Live, this electrochemical simulation software, which I really enjoy because I really didn't even know what the answer was. I just thought maybe by adjusting some of these parameters, adding a chemical step could actually demonstrate or show why you might get the peak to move a little bit more one direction while the other one kind of stays the same. So that's a hypothesis. You do need. I would need to know more about your system to actually make a good comment about that. Let's see. Okay. So that was that question. We have a new question from Cross Hero. Is it recommended to use a small potentiostat powered by a battery? I'm only doing a chronopotentiometry with minus 0.5 milliamps for 1 hour at max. So,
I mean, the thing, I guess it's a interesting question because
yeah.
I don't, what is it being powered by a battery matter? You try to use it remotely,
Yeah.
to power, or is it just the time, of your experiment that's relevant? Like, are you having interference from plugging in a potentiostat to the wall outlet, right? Or do you not have a wall outlet because you're doing an experiment somewhere?
Field testing.
Yeah, something like that, right? If you have portable potentiostat in the field, something like that, maybe that's why you'd need to run it with a battery. Intrinsically, I don't have any reason to say yes or no to this question, especially from the perspective that 1 hour isn't that long. So you could, and it depends. I guess where it is or whatever. And these values, half a milliamp. Potentiostat is using a battery as a power source. Yeah, I understand, but the point is, I don't know that there's any reason to or not to use a battery. It's, so to say, a mobile potentiostat.
Okay. All right. So you want it to be mobile.
Yeah, I mean, there's nothing wrong with that for sure.
We've done that.
yeah, for sure. I mean, that's perfectly reasonable. I think it's just a matter of if you have a battery that can power your potentiostat for an hour or more, right? There's no. I think that's perfectly reasonable. There's a lot of I shouldn't say a lot, but there are some devices that either are self-powered or you can run them on a battery power source. Either because, like I said, it can really fully float your potentiostat more if you're doing low current measurements. This can be really quite useful, in particular because there can be interference from the power grid or whatever if you're plugging into the wall in some cases. And then, if it's mobile, if you're outside, you're out in the middle of the woods, you're on top of a mountain, and you need to run cyclic voltammetry or chronopotentiometry. You can power your device with a battery and do all the electrochemistry that suits you.
Yeah, I would just check the voltage of your. So the potentiostat usually has some kind of power ratings for just running by itself. So make sure you know what that is and that your battery can satisfy that power requirement. And it's the current times the voltage. So and hopefully your chronopotentiometry experiment doesn't generate a ton of voltage, because otherwise it's like, well, then it's going to use more power or something, or it's going to measure that kind of potential. So that's the only thing to think about. But yeah, I think you can do it, definitely. Let's see. We have a question from Oluslo. Hello, doctors. I understand that multiplying the average voltage by specific capacity of the GCD gives my energy density. However, it is only based on the mass of the cathode. How do I include anode?
You don't.
You don't.
So typically you only have the cathode because the cathode's the limiting reagent. It's the limiting side. So a cathode will have, I don't know, 180 milliamp hours per gram capacity. The anode is almost always higher capacity. Even carbon, which is the standard material, is 372. So it's why the cathode is also usually twice as thick as the anode, because you need more material per gram, right? So you're going to get the same capacity. But the capacity that your battery has, right, the specific capacity, the number of amp hours or amp hours per gram that you multiply by your voltage, and you get like watt hours or watt hours per gram. That's your specific, I guess, power density, energy density. Sometimes those are used interchangeably, right? But basically similar phenomenon here. You don't include the anode per se. You're basically whatever the lower amount of whatever the capacity of the battery is determined by the lower of the two. I mean, ideally they'd be the same, right? Like the anode and the cathode. But if you have an anode that has 1,000,000 amp hours per gram or whatever, it doesn't matter because it's only going to be able to charge and discharge as much as the cathode allows. Your whatever one can, whatever anode or cathode, which usually it's the cathode, has a lower specific capacity is the rate at which the battery will function. So you don't really use the anode for that reason.
Okay.
Or sorry, perhaps I should say it necessarily includes both the anode and the cathode at that capacity level, right? It's just that you wouldn't say the battery has this much energy as it relates to a very high capacity anode if that anode isn't actually contributing all of its capacity to the battery, because it can't. Which is why when you test really high capacity anodes like silicon or tin or things like this, have like 4,000 milliamp hours per gram. We do it against lithium metal because lithium metal has an infinite amount of capacity. I mean, not really, but right, a stick of lithium as the other electrode for a one-sided, half cell allows you to test the full capability of a material, right? Because then the limiting factor will never be the lithium metal itself; it'll be the other thing. But in a real battery, one side has to be limiting, and it's almost always the cathode.
That's very interesting. Well, I guess that's all the questions we've had. Let's see. Well, it's a little early, but we could call it a day.
I think we could call it a day.
Yeah. Well, thank you all for tuning in. Next week we will not be in. There will not be a live stream. But the following week we should be here.
Yep.
If you're at the ACS meeting, definitely come to the Pine Research booth. I don't remember the number, but we are in the exhibit hall.
I have no idea. Yeah.
Yeah, I know. And it's like I put like the number on all of the no one even finds it by number. Well, I think it.
Do they find it by number? They just walk in and find us if they're looking for us.
Yeah, I mean, usually there's like the two. It's like you can go by the hundreds to find. It has rows of like 200, 300, 400, and as long as you know
I bet
that,
I can find the booth number.
Yeah, I think
I'm looking.
Yeah, actually,
it's 400 something.
It's 400 something.
I think so.
Yeah.
Wait, wrong conference. Nope, not that one.
Yeah, let me see if
wrong conference. Not 400.
Not 400.
Nope.
I'm like,
Nope.
I know our booth number is 2724.
Okay.
2724. So
very nice.
So I don't know if it's like the 2700 will be the row, but either way, that's the booth number 2724.
Come see us.
We'll be there. If you're in town, enjoy New Orleans and come visit us at Pine.
Yeah. Well, anyway, we'll see you everybody in 2 weeks. And if you have questions before then, put them as comments to this video or something, and we'll answer them when we get back. And yeah.
Yeah.
Take care, everybody.
Bye.